see. So the same formula which is given on page number 72 have written here. Simplify, substitute all the values. Simplify this, we'll get our tau v value is equal to 0.77 Newton per mm square. This is how we calculate the nominal shear stress. After this, we'll go for the percentage of tension steel reinforcement, that is denoted as PT. For this, we have the formula 100 into A strip provided divided by B into D. This formula is given on page number 73, table number 19. So, substitute all the value, simplify this, we'll get PT is equal to 1%. So, now calculate the shear strength of concrete, that is tau c denoted as tau c, by using PT value and FCK value, and with the help of table number 19 that's given on page number 73, we'll calculate the tau c value. So we'll see. So table number 19, design shear strength of concrete, that is tau c Newton per mm square. For calculation of tau c, we need to calculate the PT value. Why? Because this column contains the value of our PT value. To find out the tau c value, it is necessary, so that we need to calculate the percentage of tensile steel reinforcement to calculate the tau c value. So our PT value is, which we have got, is 1%. So for 1% we have the concrete value, that is 0.62. So we no need to do the interpolation because our value is getting directly. So for 1 we have the concrete value 0.62. So no need to do the interpolation method. So our tau c value is 0.62. Tau c value is 0.62 Newton per mm square. This is how we calculate the shear strength of concrete. And the next step is to comparison of tau c and tau v. So comparison of tau v and tau c. So our tau v value is 0.77 Newton per mm square, which we have calculated, and our tau c value is, that is 0.62 Newton per mm square. So our tau v value is greater than tau c value. So therefore our tau v value is greater than tau c. When tau v value is greater than tau c, shear reinforcement is needed. We need to calculate the shear reinforcement. For that, as per cos 40.4, page number 72, what it says. So page number 72, cos 40.4, design of shear reinforcement. Let's see what they have said. When tau v exceeds tau c given in table number 19, shear reinforcement shall be provided in any of the following forms. What they have said? They have said when our tau v value is greater than tau c, we need to provide the shear reinforcement, that may be in the form of vertical stirrups or bent upwards along with stirrups, or inclined stirrups. In the form of these three, we need to provide reinforcement. So what they have said here, shear reinforcement shall be provided to carry a shear equal to Vu is equal to tau c BD, tau c into B into D. The strength of shear reinforcement, that is VUS, shall be calculated as below. For vertical step, they have given the formula. By using this formula, we will calculate the vertical stirrups. And now we need to calculate the shear carried by concrete. For that, we have the formula VUC, that is shear carried by concrete, is equal to tau c into B into D. Substitute all the values, simplify this, we'll get 77,500 Newton, that is nothing but 77.5 kilonewton. after the calculation of this, we'll go for we also need to calculate shear carried by stirrups, that is denoted as VUS. For this we have the formula VU minus VUC, shear carried by concrete. Substitute all the value, we'll get 19.31 kilonewton. So after the calculation of shear carried by concrete and shear carried by stirrups, we need to calculate the spacing of stirrup. Spacing of stirrups should be calculated. For that we have the formula that is given on page number 73. VUS is equal to 0.87 FY ASV D divided by SV. This is given on page number 73. So for that we need to, so I'm moving this to here and shifting this to, that is SV is equal to 0.87 FY ASV D divided by SV. So now we need to calculate the ASV. For this ASV, again we need to assume the two legged vertical stirrups of 8 mm by bars. We need to assume the diameter. So I am assuming 8 mm. ASV is equal to 2 into pi by 4 into 8 square, that is diameter. I have taken 8. Simplify this, we will get 100.53 mm square. So now substitute this ASV value in this formula. So substitute all the values, simplify this, we will get 939.83. And again what we need to do for spacing of stirrups, from page number 47 and 48 what they have said. Page number 47. The maximum spacing of shear reinforcement measured along the axis of the member shall not exceed 0.75 D for vertical stirrups. What they have said? They have said our spacing of stirrups should not be greater than 0.75 D for vertical stirrups, and D for inclined stirrup at 45 degree, where D is the effective depth of the saddle. So in no case shall the spacing exceed 300 mm. And what they have said? They have said our spacing value should not be greater than 300 mm. So by using these two, we will calculate the spacing of stirrups, these two rules. So as per our codal rule, SV is should not be greater than 0.75 D. So SV is equal to 0.75 into D. Simplify this, we will get 375 mm. So one more codal rule, SV should not be greater than 300 mm. So that our SV is 300 mm. So they have said our HP value should be least of these three. So which is least for this? So 300 mm is the least value. So they have said our spacing of stirrup should be least of these three. So 300 mm is least. I am taking our SV value is equal to 300 mm. So provide two LVS of 8 mm pi bars at 300 mm center to center. This is how we calculate the spacing of stirrups. And step 9, next step is to calculate the development length. For that, as per clause 26.2.1, page number 42, what it says, we will see. This is the page number 42, clause 26.2.1, development length of bars. The development length, that is denoted as LD, is given by using this formula. We will calculate the development length. LD is equal to pi into rho s divided by 4 into tau BD. So using this formula, we will calculate the development length. Or pi is the nominal diameter of the bar and rho s stress in bars at the section considered at design load, and tau BC design bond stress. Tau B is nothing but design bond stress. and they have said something here. They have given for defined bars conform to IS 1786, this value shall be increased by 60%. What they have said. So whatever we are going to use as a design bond trace, that is tau BD, these values again increase by 60%. So for example, our our grade of concrete is, for example, 20 M20. For this, our tau BD value is 1.2. This value is again going to increase by 60%. The same formula I have written, which is given on page number 42. So our rho s value is equal to 0.87 Fy. The tau BD value for M20 design bond trace value is 1.2 for our M20 concrete. So tau BD is equal to 1.2 Newton per mm square from clause 26.2.1.1, and deformed bars increase by 60%. That is nothing but tau BD is equal to 1.2 into 1.6. So substitute all the values in this formula. So after simplifying, we'll get our LD, length of the development length value, is equal to 940.23. So I'm making it approximate value, that is 950 mm. So this is how we calculate the development length, and this is the last step of our design. And next step is to reinforcement details. So this is the our cantilever beam design. So 4 numbers of 20 mm pi bars. This is the main bar. So I have provided at the top because our tension reinforcement comes on the top because it is cantilever beam. So I have provided here, and 2 numbers of 12 mm pi bars, that is anchor bars, it comes bottom side, and two-legged vertical stirrups of 8 mm pi bars at distance 300 mm center to center. I have provided here. So our clear span value of beam is 3.25 meter, and overall depth of the beam is 550. So this is the development length which we have calculated, that is 950 mm. So I have bent here 90°. So we cannot provide directly 950 mm because our overall beam depth is 550 mm. So that I have bent 2 times, here 190°, and here also 2 times I have bent. So this is the cross section diagram of a beam. 4 numbers of 20 mm pi bars at tension zone, and at bottom side 2 numbers of 12 mm pi bars at bottom side. The overall depth of the beam is 550 mm. So this is the stirrups, 2-legged vertical stirrups of 8 mm pi bars at 300 mm center to center distance. This is how we design the, this is how we show the reinforcement details after the design. So I have shown step by step process of design of cantilever beam. If you understood this problem, like it, share it, and subscribe for the more videos. Thank you.